Okay, I hope we are connected, but let me just check. I'm not able to see it right now, so I'm not sure if I'm live or not. Okay, yeah, so I'm live. So last time we were at page number 44 and we were looking at a code piece which looks fine. We don't need to look at it. We also did top down design, stepwise refinement. Now we are at the summary of this chapter, so we can just read it through really fast and then we can go to the next chapter. We can finish that today. So, important points in this chapter include: in the 25 years of its existence, the C programming language has become one of the most widely used languages in the world. A typical C program consists of comments, library inclusions, program level definitions, function prototypes, a function named main that is called when the program is started, and a set of auxiliary functions definitions that work together with the main program to accomplish the required task. Variables in a C program must be declared before they are used. Most variables in C are local variables which are declared within a function and can only be used inside the body of that function. A data type is defined by the domain of the values and a set of operations. C includes several predefined types that allow programs to store data of several different types, such as integers, floating point numbers, booleans, and characters. In addition to these built in types, the standard library defines the type string, which is treated in this book as if it were an integral part of the language. The easiest way to read input data from the user is to call functions in the simplified IO library SimpIO, which defines such functions as getInteger, getReal, and getLine, and values. Insert the values into the standard cout stream. Otherwise, we also have if, switch, while, for. We have done that. We have return statements in the functions. If we don't have a return statement, then it's called procedure. There are some review questions right here. What is the difference between a source file and an object file? Source file contains the code, an object file contains the machine code. What characters are used to mark comments in a C program? That's double forward slash or forward slash star star forward slash. In an include line, the name of the library header file can be enclosed in either angle brackets. What is the difference between the two forms of punctuation? So we use double quotation marks when it is a private library, otherwise we use the angular brackets. How would you define a constant called centimeters per inch with the value 2.54? We will make it const float centimeters per inch equals 2.54. What is the name of the function that must be defined in every C program? That's main. What is the purpose of inserting endl into the output stream? To hit enter after the line to go to the next line. What four properties are established when you declare a variable? Do you mean? What four properties are established when you declare a variable? Not sure what they are talking about here. So let me ask. Identifier, data type, value, and scope, which is the visibility. Okay, that makes sense. Indicate which of the following are legal variable names in C++. X, Formula 1, average rainfall, tiny. A reasonably long variable name, um, beforehand, this one also. What other two attributes that define a data type? Oh, oh, I know. A data type has two attributes. It has operations which we can do with it, and it has the value of it. Like those two things. Yeah, the value and the operations I know. Let's just check. It's also saying size. That's fine. What is the difference between the types short, int, and long? It just stores. It's just the way it stores the maximum amount into it. What does the ASCII stand for? American Standard Code. Who remembers that? Information interchange. Yeah, that's right. List all the possible values of type bool, true and false. What statements would you include in a program to read a value from the user and store it in a variable x, which is declared as a double? So we'll first say double x and then we'll do c in x. Suppose that a function contains the following declarations. Write a statement that displays the values of each variable on the screen. Indicate the values and types of the following expressions. Int, still int, float, float, int, int. What is the difference between the unary minus and the binary subtraction operator? Unary minus is minus minus, it's used on one variable only, but the binary subtraction is used in two variables. You subtract one from another one. What does the term truncation means? Truncation means it will remove the if you're doing a division like 19 divided by 5, so the answer will be 3, not 3 point something, because it will truncate by itself. It will remove everything after the decimal point. Calculate the result of each of the following expressions. I mean, do I need to? No. How do you specify a shorthand assignment operation? Plus equals, minus equals, like that. What is the difference between expressions plus plus x and x plus plus? The only difference is when you are putting it with another variable and reassigning it to that variable, then the difference will make sense, because x plus plus will first assign the x and then increment the value, but plus plus x will first increment the value and then assign it to the other variable, so the increment value will be assigned. What does the term short circuit evaluation mean? Short circuit means that in the logical operators you can do short circuit, because even if the first condition is true, then the OR will give the whole thing as true. If the first condition is false, then the AND will give the whole answer as false. So you don't need to check the next condition basically. Write out the general syntactic form for each of the following control statements: if, switch, while, for. Describe in English the general operation of the switch statement. The general operation of the switch statement is to check a condition, and based on that, if we have multiple values to check for that, and we do multiple things. What is sentinel? Oh, sentinel is basically the ending point of the for loop up till which you are going. What for loop control line would you use in each of the following situations? Counting from 1 to 100. Yeah, we can do for I equals to 1, I less than 101. Counting by 7 starting at 0 until the number has more than 2 digits. Oh. So then you will do I equals to 0, I less than 100, and then I plus equals to 7, counting backwards by 2 from 100 to 0, so I equals to 100, I greater than equals to 0, and I minus equals to 2. What is the function prototype? That's like a function definition. You put the first line and you put the parameters and the name of the function, the return type and all. But then instead of putting the function, what is that called? The body of the function, we just put a semicolon and end it there. In your own words, describe what happens when you call a function in C++. We go inside that function, we execute everything. If that function returns something, then that return will come at the same line where we have called that function. What is meant by the term stepwise refinement? So we basically keep on doing the decomposition and then refine. Programming exercises. Write a program that reads in a temperature in degrees Celsius and display the corresponding temperature in degrees Fahrenheit. Okay, I'm not gonna do that. Write a program that converts a distance in meters to the corresponding English distance in feet. Okay, that's fine. According to legend, this is all maths. When he was in elementary school, Gosh was asked by his teacher to compute the sum of the numbers between. That's simple. Write a program that reads in a positive integer n and then calculates and displays the sum of first and odd integer. Okay. Write a program that reads in a list of integers from the user until the user enters the value 0 as sentinel. When the sentinel appears, your program should display the largest value in the list. Okay, that makes sense. Using the digit sum function from the section entitled the while statement as a model, write a program that reads an integer that displays the number that has the same digits in reverse order address. Okay. Yeah, we can do that. Greek mathematicians took a special interest in numbers that are equal to the sum of their proper divisors and they are also called perfect numbers. For example, write a predicate function which is a true-false function is perfect, which returns this. Okay, yeah, we can do that. Every positive integer greater than 1 can be expressed as a product of prime numbers. This factorization is unique, called prime factorization. For the number, note that write a program to display the prime factorization of a number n. Yeah, I think I can do that. When a floating point number is converted to an integer in C++, the value is truncated by throwing away any fraction. Thus, when this is converted to an integer, the result is 4. In many cases, it would be useful to have the option of rounding a floating point value to the nearest integer. For a positive floating point number, the rounding operation can be achieved by adding 0.5 to x and then truncating the result to an integer. If the decimal fraction is x is less than 0.5, the truncated value will be integer less than x. If the fraction is 0.5 or more, the truncated value will be the next larger integer, because truncation always moves towards 0. Negative numbers must be rounded by subtracting 0.5 and truncating instead of adding 0.5. Write a function round x that rounds a floating point number x to the nearest integer. Show that your function works by writing a suitable program to test it. We can do that. There's a Leibniz series which we need to write, I think. Okay. These are all mathematical questions. Why? Don't want to do mathematical questions. Okay, we are on chapter 2. Let's not do all the questions right now. I'm not gonna do that. Okay. But let's do the chapter 2 data types in C++. It is a capital mistake to theorize before one has data. Insensibly, one begins to twist fact to suit theories instead of. Okay, that was just a quote. So, chapter 1 of this text is a capsule summary of the features of C necessary to code the algorithm structure of a program. The algorithm structure, however, represents only part of the story. It is equally important to consider the structure of the data, like control statements and function calls, each of which can be nested hierarchically to represent increasingly complex algorithmic structures. Data types in a language also form a hierarchy. The base of the hierarchy is composed of the atomic types that were introduced in chapter 1, coupled with a new class of atomic types called enumeration types that are introduced in the following section. Starting from this base, you can extend the hierarchy using the following mechanisms for creating new types from existing ones. Pointers. A pointer is simply the internal machine address of a value inside the computer's memory. Okay. C++ allows you to work directly with pointers as data and makes them part of the type hierarchy, which means that you can define new types whose domains consist of pointers to values of some existing type. Arrays is an ordered collection of data values, each of which has the same type. A record is a collection of data values that represent some logically coherent whole. The individual components are identified by the name rather than by order and maybe of different types. Each of these types is described in detail in a separate section later in this chapter. For now, the main point is that you can combine these mechanisms to generate new types as whatever level of complexity the program requires. You can, for example, create new types that are pointers to records containing arrays or any other nested structure you choose. The hierarchy of types in a program defines its data structure. Enumeration types. Before moving on to the question of how to create new types from existing ones, it is important to complete the set of atomic types that form the basic of the type hierarchy. The most common atomic types are integers, floating point numbers, characters, and so on. Like many languages, however, C++ make it possible to define new atomic types by listing the elements that constitute their domains. Such types are called enumeration types. Okay, so in this text, new enumeration types are defined using the following syntactic form: enum, and then put the name, and then put the element list. Where element list is a list of identifiers which are called enumeration constants, and name is the name of the new type. For example, the following enumeration type defines the four principal compass directions. Similarly, the following definition introduces the type color T, which consists of the six primary and secondary colors available on the. Okay, fine. Once you have defined an enumeration type, you can declare variables of that type just as you do with any of the built-in types. For example, the declaration. Oh, this is so cool. So if we make enum and have a lot of values inside it, like we do January equals to 1, and then after that we just write February till the December, it knows that the February will be 2 and so on. It will keep on adding 1 and 1 and 1 to every further month. Defining an enumeration type is in many ways similar to defining named constants. In the month T example, you could achieve a similar effect by making the following definitions. Inside the machine, the two strategies produce the same result. Every element of the enumeration type is represented by an integer code. From the programmer's point of view, however, defining separate enumeration types has three advantages. The programmer does not need to specify the internal codes explicitly. The fact that there is a separate type name often makes the program easier to read because declarations can use a meaningful type name instead of the general purpose designation int. A C++ compiler does some rudimentary checking for enumeration types. For example, an integer value cannot be assigned to any num variable without a typecast, which helps to draw attention to possible mistakes such as assigning a value out of range for the enumeration. On many systems, programs that use enumeration types are easier to debug because the compiler makes the names of the enumeration constants available to the debugger. Thus, if you ask it about a value of the type month t, a well designed debugger would be able to display the value January instead of the integer constant 1. Scalar types. In C++ enumeration types, characters and the various representations of integers form a more general type class called scalar types. When a value of a scalar type is used in a C++ expression, the compiler automatically converts it to the integer used to represent that value. The effect of this rule is that the operations you can perform on values of any scalar type are the same as those for integers. As an example, suppose that you want to write a function right from dir that takes a direction t and returns the direction you would be facing if you turned 90 degrees from the starting point. Thus, this should return right from north should return east because the direction appears in order removed. West, which has 0 instead of 4 as underlying value, as it in this case we will do. Okay. Okay, I was just looking at this question and I'm done looking at it. This looks fine. Let's move to another topic called data and memory. So, before you can understand C++ type system in any detail, you need to know how information is stored inside a computer. Every modern computer contains some amount of high-speed internal memory that it is that is its principal repository for information. In a typical machine, that memory is built out of a special integrated circuit chip called RAM, which stands for random access memory. Random access memory allows the program to use the contents of any memory cell at any time. The technical details of how the RAM chip operates are not important to most programmers. What is important is how the memory is organized: bits, bytes, words. At the most primitive level, all data values inside the computer are stored in the form of fundamental units of information called bits. A bit is a unit of memory that has only two possible states. If you think of the circuitry inside the machine, it were a tiny light switch, you might label those states as on and off. Historically, the word bit is a contraction of the binary digit, and it is therefore more common to label those states using the symbol 0 and 1, which are two digits used in the binary number system on which computer arithmetic is based. Since a single bit holds so little information, the bits themselves do not provide a particularly convenient mechanism for storing data. To make it easier to store such traditional types of information as number or characters, individual bits are collected together into larger units that are then treated as integral units of storage. The smallest such combined unit is called a byte and is large enough to hold a value of type char, which typically requires 8 individual bits. On most machines, bytes are assembled into a large structure called words, where a word is usually defined with the size required to hold a value of type int. Some machines use 2 byte words, 16 bytes. Some use 4 byte words, 32 bits, and some use less conventional sizes. Memory addresses. Within the memory system, every byte is identified by a numeric address. Typically, the first byte in the computer is numbered as 0, the second is numbered as 1, and so on up to the number of bytes in a machine. For example, if your computer has 4 megabytes of memory, which actually means 4 multiplied 2 raised to the power 20, or the address of the memory cells would look like this. Each byte of the memory is large enough to hold one character. For example, if you were to declare the character variable ch, the compiler would reserve 1 byte of storage for that variable part as part of the current function frame. Suppose that this byte happened to be an address 1000. If the program then executed the statement, the internal representation would be stored in the location 1000. Yeah, that makes sense. In most programming applications, you will have no way of predicting the actual address at which the particular variable is stored. If the preceding diagram, the variable ch is assigned to address 1000, but this choice is entirely arbitrary. When your program makes a function call, the variables within the function are assigned to memory locations, but you have no way of predicting the address of those variables in advance. Even so, you may find it useful to draw pictures of memory and label the individual equations with the address beginning at a particular starting point. These addresses, even though you choose them yourself, can help you to visualize what is happening inside the memory of the computer as your program runs. Values that are larger than a single character are stored in consecutive bytes of memory. For example, if an integer takes up 4 bytes on your computer, that integer requires 4 consecutive bytes of memory and might therefore be stored in the shaded region of the diagram. The data values require multiple types, and multiple bytes are identified by the address of the first byte. So the integer represented by the shaded area is the word stored at address 1000. When you write a C++ program, you can determine how much memory will be assigned to a particular variable by using the size of operator. The size of operator takes a single operand, which must be a type name enclosed in the parentheses. and it returns the number of bytes required to store the value of that type. And if the operand is an expression, the size of returns the number of bytes required to store the value of that expression. Returns the number of bytes required to store a value of type int. The expression of returns the value. Yeah. Okay, we are on the pointers. One of the principles behind the design of C++ was that programmers should have as much access as possible to the facilities provided by the hardware itself. For this reason, C++ makes the fact that memory locations have addresses visible to the programmer. A data item whose value is an address in memory is called pointer. In many high-level programming languages, pointers are used sparingly because those languages provide other mechanisms that eliminate much of the need for pointers. The Java programming language, for example, hides pointers from the programming altogether. In C++, pointers are pervasive, and it is impossible to understand C++ programs without knowing how pointers work. In C++, pointers serve several purposes, of which the following are the most important. Pointers allow you to refer to a large data structure in a compact way. Data structures in a program can become arbitrarily large. No matter how large they grow, however, the data structures still reside somewhere in the computer's memory, therefore have an address. Pointers allow you to use the address as a shorthand for the complete value. Because a memory address typically fits in 4 bytes of the memory, this strategy offers considerably space savings where the data structures themselves are large. Pointers make it possible to reserve new memory during program execution. Up to now, the only memory you could use in your program was the memory assigned to the variables that you have declared explicitly. In many applications, it is convenient to acquire new memory as the program runs and to refer to that memory using pointers. This strategy is discussed in the section dynamic allocation later in this chapter. Pointers can be used to record relationships among data items. In advanced programming applications, pointers are used extensively to model connections between individual data values. For example, programmers often indicate that one data item follows another in a conceptual sequence by including a pointer to the second item in the internal representation of the first. Using addresses as data values. In C++, any expression that refers to an internal memory location capable of storing data is called I value, pronounced as L value. Oh, L value, not I. They are just talking about something called L value, which refers to an internal memory location which is going to be constant, but it can store different things at different level of the code, but it's going to be of the same type every time, and it will require different amounts of memory based on what type it is going to store. And the address of the L value is a pointer value which can be stored in memory and manipulated as data. Declaring pointer variables. As with all other variables in C++, you must declare pointer variables before you use them. To declare a variable as a pointer, you precede its name with an asterisk in a standard declaration. For example, the line int star p declares a variable p to be the conceptual type pointer to int. Similarly, the line char star cptr is a pointer to char. These two types, pointer to int and pointer to char, are distinct in C++, even though each of them is represented internally as an address. To use the value at that address, the compiler needs to know how to interpret it, and therefore requires that its type be specified explicitly. The type of the value to which the pointer points is called the base type of that pointer. Thus, the type pointer to int has int as its base type. It is important to note that the asterisk used to indicate that a variable is a pointer belongs syntactically with the variable name and not with the base type. Like I've seen people using asterisk just with the data type and in the middle of the data type and the variable and on the variable also. The correct way to use the asterisk is on the variable name because uh, it belongs with the variable name and not with the base type. So when you are declaring two pointers together like int star p1 comma p2, you need to write the asterisk with the p2 also, otherwise it will just be declared as an integer, not a pointer to integer. So that's important. The fundamental pointer operations. C++ define two operations that allow you to move back and forth between values and pointer to those values. Ampersand means address of and asterisk mean value pointed to. Ampersand means address of and the asterisk means value pointed to. The ampersand operator takes an L value as its operand and returns the memory address in which the L value is stored. The asterisk operator takes a value of any pointer type and returns the L value to which it points. This operation is called dereferencing the pointer. The asterisk operation produces an L value, which means you can assign a value to the dereferenced pointer. The easiest way to illustrate these operators is by example. Consider the declarations int x, y, int star p1, star p2. These declarations allocate memory for 4 words, 2 of type int and 2 of type pointer to int. For concreteness, let's suppose that these values are stored in a machine address indicated as follows. You can assign values to x and y using assignment statements. So it will look like this. To initialize the pointer variables p1 and p2, let's assign the address of x and y to p1 and p2. Okay, that makes sense. The arrows in the diagram are used to emphasize the fact that the values of the variables p1 and p2 point to the cells indicated by the heads of the arrows. Drawing arrows makes it much easier to understand how pointers work. But it is important to remember that pointers are simply numeric addresses and that there are no arrows inside the machine. To move from a pointer to the value it points to, you can use the asterisk operator. For example, star p1 indicates the value in the memory location to which p1 points. Moreover, since p1 is declared as a pointer to the integer, the compiler knows that the expression star p1 must refer to an integer. Thus, given the configuration of the memory illustrated in the diagram, star p1 turns out to be another name for the variable x. It's true. Like the simple variable name x, the expression star p1 is an L value and you can assign new values to it. Executing the assignment statement like this. Change the value in the variable x because that is where the p1 points. After you make this assignment, the memory configuration is this. You can see that the value of p1 itself is unaffected by this assignment. It continues to hold the value 1000 and therefore still points to the variable x. It is possible to assign new values to the pointer variables themselves. For instance, the statement p1 equals to p2 instructs the computer to take the value obtained in the variable p2 and copy it to the variable p1. The value contained in p2 is the pointer value 1004. If you copy this value, now p1 and p2 both point to the variable y. In terms of the operations that occurs inside the machine, copying a pointer is exactly the same as copying an integer. The value of the pointer is simply copied, unchanged to the destination. From a conceptual perspective, the diagram shows that the effect of copying a pointer is to replace the destination pointer with a new arrow that points to the same location as the old one. So the effect of assignment is to change the arrow leading from point p1 as it points to the same memory address as p2. That's called pointer assignment. You can also do value assignment, which is represented as this. Star p1 equals to star p2. So now it will copy the value from the memory location p2 and put it into the location address by p1. There is one special pointer called null. So in many pointer applications, it is useful to be able to store in a pointer variable at a special value indicating that the variable does not in fact point to any valid data. At least for the present. Such a pointer variable is called a null pointer and its value is assigned the address 0. The special constant called null can be used for this purpose. It is important not to dereference a null pointer with the star operator. The intent of the null value is to indicate that the pointer does not point to the valid data. So the idea of trying to find the data associated with the null pointer does not really make sense. Unfortunately, most compilers do not produce programs that explicitly check for this error. If you dereference a null pointer, many computers will interpret the value as 0 and return whatever data value is stored at as address 0. Oh, it will interpret the 0 value as an address and it will return whatever is present at the address 0. If you happen to change that value by performing value assignment through a null pointer, the program can easily crash, giving no hint of the cause. The same problem can arise if you use pointer variables whose values have not been initialized. The use of null pointer will be introduced in this text as they become relevant to the particular application. For now, the important thing to remember is that this constant exists. We are on the arrays now. The array is a collection of individual data values with two distinguishing characteristics. An array is ordered. You must be able to count off the individual components of an array in order. Here is the first, here is the second, and so on. An array is homogeneous. Every value stored in an array must be of the same type. Thus, you can define an array of integers as an array or an array of floating point numbers, but not an array in which both are mixed. Each of the values in an array is called an element, and it's like in a single box. Each array has two fundamental properties: the element type, which is the type of the value that can be stored in the elements of the array; the array size, which is the number of elements that the array contains. When you declare the array, you need to declare it like type, the name of the array, and the square brackets and the size inside it. Where type is the type of each element in the array and the name is the name of the array variable and size is constant indicated the number of elements allocated to the array. Declares an integer array with 10 elements, each of the type int. You should specify size as symbolic constant rather than implicit integer. Okay, it's a good habit to specify the size as a symbolic constant rather than an explicit integer so that the array size is easier to change. Thus, a more conventional declaration would look like this. You can represent this declaration pictorially by drawing a row of 10 boxes and giving the entire collection name int array. Each element in the array is identified a numeric type called its index. An index starts from 0 until the end. As is the case with any variable, you use the name of the array to indicate to other readers to program that what sort of values is being stored. For example, suppose that you want to define an array that was capable of holding the scores. So you can name it as scores, and you can store it as a double type. Array selection. To refer to a specific element within an array, you specify both the array name and index, and you do it like this. Within a program, a selection, this is how you can change it. Thus, if the first judge 0, still since C++ counts array elements beginning at 0, so you change it like this, when you change the rest as this. In working with arrays, it is essential to understand the distinction between the index of an array element and the value of that element. The real power of the array selection comes from the fact that the index you need not be constant, so you can do it like this using a for loop. This is good. Effective and the allocated sizes. At the time you write a program, you often will not know exactly how many elements an array will contain. The number of array elements usually depends on the user's data. Some users may require large amounts of array storage, while others needs less. Unfortunately, you can't simply declare an array as array bounds must be constant. The usual strategy for solving this problem is to declare an array that is larger than you need and use only part of it. Thus, instead of declaring the array based on the actual number of elements, which often do not know in advance, you define a constant indicating the maximum number of elements and use that constant in the declaration of indicating the maximum of the array. On any given use of the program, the actual number of elements is always less than or equals to this bound. When you use this strategy, you need to maintain a separate integer variable called allocated size. The number of elements actively used is called the effective size. The allocated size and the effective size. As an example, suppose that you want to change the declaration of array scores, and you want it like this. To keep track of the effective size, you would need to declare an additional variable as follows called n judges, passing arrays as parameters. Functions in C++ can take entire arrays as parameters. When they do, it is common, particularly if the allocated and effective sizes must be different, to omit the maximum bound of the parameter declaration and use empty brackets instead. Okay. For example, the following function takes an array of type double, an integer indicating the effective size of the array, and returns the mean or arithmetic average. Makes sense. When a function takes an array argument, the value of that argument is not copied in the way that simple variables are. Instead, the function always gets a pointer to the array, which means that the storage used for the parameter array is shared with that of the actual argument. Changing the value of an element of the parameter array therefore changes the value of the corresponding element in the argument array. So if we are passing an array to the function, it's always passed as a reference, not the value. The use of arrays as parameters is illustrated in the gimjudge.cpp program shown in figure 2.1. Note that there is some function they have made. Initialization of arrays, you can initialize it using curly brackets with, yeah, and sometimes you don't need to mention the number of elements inside it. When the compiler encounters a declaration of this form, it counts the number of initializers and reserves exactly that many elements for the array. In the digits example, there is little advantage in leaving out the array bound. You know that there are 10 digits, and the new digits are not going to be added to the list for arrays whose initial values may need to change over the life cycle of the program. Having the compiler compute the array size from the initializers um, is useful for program maintenance because it frees the programmer from having to maintain the element count as the program evolves. For example, imagine you're writing a program that requires an array containing the names of all the US cities with populations of over 1 lakh, 1 million. Taking data from 1990 census, you could declare and initialize big cities as a global array using the following declaration. Okay. When the figures are in from the 2000 census, it is like the Phoenix and San Antonio will have joined in the list. If they have, you can then simply add their names to the initializer list. The compiler will expand the array size to accommodate to the new values. Note that a comma follows the last initializer for the big cities array. This comma is optional, but it is good programming practice to include it. Doing so allows you to add new cities without having to change the existing entries. If you write program that uses big cities array, you will probably need to know how many cities in the list contains. The compiler has this number because it counted the initializers. Okay, let's have a look at this program to average a set of scores. So you have some constants defined, you have the prototypes of the functions defined, and then let's look at the functions. We are passing the scores array, and we are finding the and what does the get score does? It gets the judges. The question is how to make that information available to the program. In C++, there is a standard idiom for determining the number of elements in an array whose size is established by static initialization. Given my array A, the number of elements in A can be computed using the expression size of A and the size of A of 0. That will give you the number of elements. Okay, makes sense. Multidimensional arrays. In C++, the elements of an array can be of any type. The elements can themselves be arrays. Arrays of arrays are called multidimensional arrays. It has rows and columns, and it's also called matrix. Yeah, so like that. Internally, C++ represents the variable mat as an array of 3 elements, each of which is an array of 3 floating point values. The memory allocated to mat consists of 9 cells arranged in the following form. Makes sense. In this two-dimensional diagram, the first index is assumed to indicate the row number. This choice, however, is arbitrary because the two-dimensional geometry of the matrix is entirely conceptual. In memory, these values from one-dimensional list, if you want to change the declaration, only the way in which you select the elements. In terms of the internal arrangement, however, it is always true that the first index varies least rapidly. Thus, all the elements of mat0 appear in memory before any elements of mat1. Yeah. Multidimensional arrays are passed between functions just as single dimensional arrays are. The parameter declaration in the function header looks like the original specify the size of each index in a parameter array except for the first. However, because leaving out the first index bound makes the declaration unsymmetrical. It is common to include the array bounds for each index in the declaration of a multidimensional array parameter. Okay, they are talking about identity matrix in which the diagonal has all the ones and the rest of them are zeros. Okay, pointers and arrays. In C++, arrays and pointers are defined in such a way that a complete understanding of either topic requires that you understand the other. Arrays, for example, are implemented internally as pointers. The operations on pointers only make sense if you consider them in relation to array. Thus, in order to give you the full picture of how arrays and pointers work, it is important to consider the two concepts together. Okay. Mhm. Because each of the elements in the array is an L value. It has an address that can be derived using the ampersand operator. Each of the elements in array is an L value. Each of the elements is an L value. Okay. Um, I think I need a little break, so I'll start the streaming again.